All right, welcome everybody. Let's do this. So lesson 15, part 3 with the broken finger, dislocated finger of Mr. G. All right, so from just a review from yesterday, that if I have some point Z, right, and I were to say, okay guys, the angle over here, let this be alpha, right, and now let's look at my W and say that this angle is, let's say, beta. Then what do we know about the angle of ZW? That this angle has to be this angle plus this angle. So this is alpha plus beta, right? So this is the argument of Z, which is the rotation. If this is alpha and this is beta, then we know that the argument or the amount of rotation for ZW has to be alpha plus beta. Whatever alpha and beta are, they could be anything. And also we figured out that, let's say the modulus of this is x and the modulus of this is y, meaning the distance from here to here is x, the distance from here to here is y, then the distance from here to here must be x times y. Okay? So this was very key from last class. What we want to do for today is that, what do we want to do? Imagine if we have a point Z and it's equal to this complex number, right? Let's say this is my Z, this is my complex number, and I say, hey, put this into polar form, right? And you make your triangle and you do your thing and you do your arc cosine theta plus I sine theta, easy money, okay? But now, imagine if we don't know where the point Z is. So Z could be anywhere. And all I'm telling you is that the modulus of Z is 3 and the degree of rotation is 30 degrees, where is this point Z? Do we have enough information to locate exactly where this point is? Okay? And that's the general idea for this lesson. So what I want you to do is, everybody take out your orange book and please go to S.71 and we should be on this page over here. Okay? So let's look at number 3. Here it's saying that, imagine if I have Z and W are complex numbers with specified arguments, right? So the argument here is the amount of rotation and the moduli, right? The distance from the point to the origin. Locate the point that represents the product of WZ on the provided axes. Before we do this, can we calculate where the point W is if we have, like this W? Where is W over here? Well, one thing we need to know first is, this argument is pi over 4. How can I convert pi over 4 into degrees? Well, this is going to be what? 180 over pi. So that's, these pi's cancel out. So 180 divided by 45, and this becomes, divided by 4, and that's 45 degrees. So I know my W has a degree, oh wow, this is very blurry. Sorry about that. Is this better? Hold on, sorry. Okay, that's better. So here, we know that we have a 45-degree angle. So we're definitely in quadrant 1, okay? And now it's saying that the distance is 3. So I know that if I have some W, right? The distance from here to here is 3, and this angle is 45 degrees. So how do I know where W is? All I need to do is use R cosine theta plus I sine theta. Here, I'm going to go backwards to figure out where W is. I know W has to equal this. So W, well, what's my R? My R is 3. And what's my argument? Well, my argument is pi over 4, or 45 degrees, plus I sine 45 degrees, right? Now, what is cosine of 45 degrees? That's a square root of 2 over 2, plus I. Let's see, this sine of 45 is also square root of 2 over 2, and I. So then, what will this be? This will be, we gotta distribute it, right? So this is 3 radical 2 over 2 plus 3 radical 2 over 2i. So this is a point. This is my point W, okay? And that's how you find, you're basically going backwards to finding the point. You have your you have your modulus, you have your argument. What I want you to do is to go backwards to find the point W, find the point Z, and then, hey, can you find WZ? Where will that be? And I want you to try and do that by yourself, okay? Best of luck.